Alright, this video is going to be an introduction to multiplication. We have already gone over in previous videos addition and subtraction and gotten into negative numbers. When we talk about multiplication, we first have to realize that it is simply shorthand for addition. Nothing more, nothing less. So when we say 3 times 4, we literally just mean what is 4 added to itself 3 times, or 3 fourths. It's important to realize that the 3 is not a separate term, but instead an instruction for how many times to add 4 to itself. We call this a coefficient. I want to point out that this is actually really similar to language, the way that you might have an adjective to describe a noun. When we say that there is a fast dog, the dog is the only object in that sentence. It's the only noun. The word fast is just simply describing the dog, just the same way 3 is describing how many 4s there are. They're not two separate things. We can see here 3 plus 3 is the same thing as 2 3s, or 2 times 3, which gets to 6. 3 times 3 would be counting up by 3. 3, 6, 9. The product of a whole number times a whole number coefficient is also called a multiple. So far, with addition and subtraction, all that we've been doing is counting by ones. If we say 2 plus 3, we mean count up 1, 2, 1, 2, 3, and we would get to 5. Now that we're dealing with multiplication, we're actually counting up by different units. So if we're counting up by multiples of 3, then we're literally counting in groups of 3. So the first multiple is going to be 3. The next multiple of 3 is 6, and then 9, 12, 15, 18, so on and so on. If we say 3 times 5 is 15, 15 is the third multiple of 5. With this in mind, we can define multiplication as the sum, or C, of A segments, each of length B. So 3 times 4 equals 12. If we have something that's 4 inches long, and there are 3 of them, then we have 4 plus 4 plus 4, or 12. It's conventional to refer to this as the product, just to help kind of separate addition and multiplication problems. But this is the sum of 3 fourths. We can therefore state 15 is the third multiple of 5. This is also the beginning of thinking about what a unit really means. For example, there are 4 cups in 1 quart. If I had a bucket of water and it had 3 quarts, how much water is in the bucket? Well, there's no necessary one way to think of it. If we think of 1 as being the quart, then there's 3 quarts. However, if we're thinking about cups, then we actually have 4 cups of water 3 times, or 4 plus 4 plus 4. There are 4 cups in a quart. So there would be 12 cups. So if I asked you how much water was in this problem, if I say a bucket had 3 quarts, well, you could say there's 3 quarts, you could say there's 4 cups, or you could go 12 cups, excuse me, or you could go further and do it in other units, like tablespoons or gallons. What I want us to do right now is to just think about what these problems actually mean. For example, 4 times 5 means 4 5s. Well, here this would mean 7 3s, or 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3. And you can pause and kind of work these out, but it's important to see that, like in this problem 4 times 5, if we actually break it down, notice that there is no 4. There just happens to be 4 5s. From there, we can talk about a couple properties. Given that multiplication really is just shorthand for addition, the properties of addition are the same for multiplication, the associative property. How you group things does not matter. And the commutative property, the order in which you multiply, does not matter. We can look at some examples and see. For example, 3 times 5 is the same thing as 5 times 3. I bet we do that on the next slide. Yeah. 2 times 3, 3 times 2, both of these equal 6. And you can think about it, if you have 2 segments of wood that are each 3 inches long, you have 6 inches. And if you have 3 segments of wood that are each 2 inches long, it's still 6 inches. You can go on and calculate these following problems and see that they all equal each other. This is a really important time to introduce a new type of notation. So far, we've talked about standard notation, which is just the typical way we think of writing numbers. And we've also talked about expanded notation, which is where we break out each place value as a separate number. We're now going to talk about scientific notation, and let's address why we even have it. This is a big number. This is how old the universe is. I don't know about you, but I cannot quickly just calculate what this number is. Scientific notation makes this easier. For example, 10 squared equals 10 times 10. And 10 to the third power equals 10 times 10 times 10. And 10 to the fourth is 10 times 10 times 10 times 10. And we can see that exponents are now just a shorthand for multiplication. So multiplication is shorthand for addition. And addition is and exponents are shorthand for multiplication. 10 to the third just means 10 times itself 3 times. And in general, whatever the exponent is, 10 to the nth power, means 10 times itself n times. We can also observe an important pattern here. Whatever the exponent is, notice 10 squared, how many zeros are there? Well, there's 2. 10 to the third is 1,000. How many zeros? There's 3. 10 to the fourth is 10,000, or 4 zeros. And in general, 10 to the nth power is going to be a 1 with n zeros. Now, we're building up to a very important property of exponents that we're going to then be able to use to kind of make sense of multiplication. 10 squared is 100. Well, that means 10 times itself, right? 10 times 10. 10 2 times. Well, 10 times 10 means 10 added to itself 10 times. So 10 squared is the same thing as 10 plus itself 10 times, which we can write as shorthand as 10 times 10, or even further shorthand and just say 10 squared. Well, notice 10 to the third is 10 times 10 times 10. Well, we already figured out what 10 times 10 is. It's 100. So we're now saying 10 hundreds, or 100 plus itself 10 times. And that, of course, gets us to 1,000. 100, 200, 300, 400, 5, 6, 7, 8, 9, 10. 10 hundreds, or 1,000. 10 to the fourth, the same pattern. This then means 10 thousands. 10 times 10 times 10 times 10, or 10 times 1,000. So 1,000 plus itself 10 times is going to get us to 10,000. Now, what about the number 50,000? Well, 50,000, if we count up by 10,000s, that's 5 10,000s, right? 10,000 plus 10,000 plus 10,000 plus 10,000 plus 10,000. Well, 10,000, let's see, how many zeros? 1, 2, 3, 4. So that's 10 to the fourth. So we have 10 to the fourth plus itself 5 times. Well, that's multiplication, right? 5 times 10 to the fourth. 10,000 5 times 10,000 plus 10,000 plus 10,000 plus 10,000 plus 10,000 is 5 times 10 to the fourth. And this right here, this is scientific notation, where you're simply recording this significant value, how many 10,000s there are, times the scientific notation. So I'm going to do one of these with us real quickly. So 80,000. Well, let's see. That's 8 10,000s, right? 10,000 has 4 zeros, so that's 10 to the fourth. And let's see, how many times are we counting up that? It'd be 1 plus 2 plus 2. Well, that's 8. So 8 times 10 to the fourth. 20. Well, there's 1 zero, right? So that's 10 to the first, or just 10. And how many? It's 10 plus 10, or 2 times 10. And we could go on and on. Okay, so now what we're going to do, 482 in expanded form. Well, that's 400 plus 80 plus 2. Now, can I write each of these in scientific notation? Absolutely. I can say 4 times 10 squared plus 8 times 10 to the first plus 2 times 10 to the 0. And notice 10 to the 0 just means 1 with no zeros, or 1. So this is 4 hundreds, right? 400 is 4 hundreds. 80 is 8 tens, and 2 is 2 ones. And this is a problem we would do as a class. So here is 396,000. There's 0 hundreds, so that was not included here. Plus 10 plus 9, or 19. Now we can write this in scientific notation. How many zeros? 1, 2, 3, 4, 5. So that's 3 times 10 to the 5th. And how many zeros are here? 4. So this is 9 10,000s, or 9 times 10 to the 4th. 6,000s. 6,000, right? 6 times 10 to the 3rd. I went ahead and put this in. There's 0 hundreds, right? Which, of course, would just be 0. 0 times anything is 0. We have 1 10 and 9 ones. So this is an exercise we would do in class. We need to point out one more thing before we can state this big property about exponents that we're building up to. And that is, notice, 10 to the 3rd is really 10 times 10 times 10. Well, what is 10 times 10? Well, that's 100, or 10 squared. So instead of saying 10 times 10, I could say that this is 10 squared times 10. Well, 10 is really 10 to the 1, right? A 1 with 1 0. So we have 10 squared times 10 to the 1st. And let's look for a pattern here. Let's see if we can notice something. 10 to the 3rd is the same thing as 10 squared times 10 to the 1st. I wonder if you see something here. Let's look at another one. 10 to the 4th is 3 tens, which is 10 to the 3rd, right? 10 times 10 times 10. 10 times itself 3 times. That's 10 to the 3rd. Times 10 to the 1st, or 10. So 10 to the 4th is 10 times 3 times 10 times 1. I wonder if we see this pattern emerging again. What do we notice about these exponents in the problem versus in the solution? And hey, 10 to the 4th, instead of doing it this way, couldn't we say it's 10 squared times 10 squared? So 10 squared times 10 squared. Do we see a pattern here? Notice, what is 3 plus 1? Well, it's 4. What is 2 plus 2? Well, it's 4. Hey, let's go back to that previous page. What is 2 plus 1? 3. And in general, we could keep showing this example over and over again, but in general, the product property of exponents says when you have two numbers that have the same base, that means that it's both of these numbers start with 10, and then it's just a different exponent. We can just add those exponents together. So 10 to the 4th times 10 to the 3rd, well, what's 4 plus 3? Oops. 4 plus 3 is 7, right? So this is 10 to the 7th. Now what we can do, and let me illustrate one more thing. If we kind of think about this, this is like, let's say here, this is 10 times 10 times 10 times 10 times 10. Well, that's 5 tens, right? That's why we can add these exponents to get to our solution. All right, so lastly, we can now extend our understanding of the associative and commutative properties of multiplication to solve more complex problems. Let's say we have 4 times 10 to the 6th times 2 times 10 to the 9th. That's this problem, but we wrote it in scientific notation. And notice how much easier this is to read than trying to read this. We don't have to count all these zeros. We know there's 9. Well, it's all multiplication, so we can get rid of the brackets by the associative property. And then we can also rearrange these terms by the commutative property. Well, what is 4 times 2? Well, that's 8. And 10 to the 9th times 10 to the 6th, well, what's 9 plus 6? It's 15. So the solution to this huge problem, I can't even imagine trying to count, what is this, 2 billion? 4 million times? Like that, I can't even, that would take forever to count. However, with just a few properties, this was an incredibly simple problem to solve. We'll do this one together real quickly. There's 6 zeros, so this is 3 times 10 to the 6th, right? This is not 1 million, but 3 million, so 1 million 3 times. And this is 20,000, so that's 1, 2, 3, 4 zeros. So this is times 2 times 10 to the 4th, yes? And I'm going to write these parentheses in here because that's technically what you should do. But we know because of the associative property, we really actually don't need them, right? The associative property says, you don't need to worry about those. And then from there, we use the commutative property. And we say, okay, it doesn't matter what order. So what's 3 times 2? Well, that's 6, right? And then 10 to the 6th times 10 to the 4th. Well, what's 6 plus 4? Yep, you guessed it. 10 to the 10th. And that would be our solution. And then here's a few other problems that you can do on your own. That is our first video on introducing concepts of multiplication. Thank you.